Let's look at some other properties of the Fourier transform, such as the translation property. So let's say we have a function f of xy and its transform f of uv. Now if we shift f of xy by x0 and y0, that the effect on the Fourier transform is multiplying each value of uv by an exponential like this. Or if we shift the transform by u0 v0, that multiplies the original function by these exponentials. And you can show that by substituting these into the equations for the discrete Fourier transform. Similarly for the continuous case. So for example, what we showed a little bit ago was shifting the Fourier transform of the image so that the zero frequency is at the center. So what we did was shift by a factor of m over 2 in the u dimension and n over 2 in the other dimension. So this new Fourier transform actually has a Fourier pair of f of xy where each point is multiplied by this power of -1 to the x plus y. To see that, we can use the translation property. This case we'll use this one, namely shifting the Fourier transform and seeing what effect that has. So let's let u0, the amount we shift by, be m over 2 and v0 be n over 2. So the Fourier pair of f of u minus u0 v minus v0, according to the translation property, is f of xy e to the j 2 pi m over 2 times x over m, and then plus n over 2 y over n. So the m's and n's cancel out, and we get e to the j 2 pi x over 2 plus y over 2, or f of xy e to the j pi x plus y. And now we're going to use, well, first let me write f of xy e to the j pi, and that whole quantity raised to the x plus y. So we use the Euler's formula that e to the j pi is cosine of pi minus j sine, or plus j sine of pi. So that's just a -1. So it's -1 to the x plus y. Okay. Another useful property is the rotation property, which says that if we rotate an image by an angle theta 0, the transform is rotated by the same amount. And you can see that, I won't do that example, but this would be one example of that. The differentiation property is useful. So you can simply by plugging into, again, the definition of the Fourier transform, you can show that taking the mth derivative in the x direction and the nth derivative in the y direction results in multiplication of the transform by these products here. So for example, the Laplacian is the sum of the second derivative of f plus the second derivative of y. So to see what that would look like on the transform, I'll just plug in 2 for those products. So j 2 pi u squared plus j 2 pi v squared, and then f of uv. So j squared is minus 1, so this comes out to be 2 pi squared u squared plus v squared f of uv. So we'll see a little bit later why this is interesting, but if you look at this piece right here and call that h of uv, so essentially I'm taking h of uv and multiplying by my original transform f of uv. So h is a filter. It's the transform of a filter, and it has kind of a quadratic behavior where if I look at a profile of that through the u, it kind of looks like this. So it's very small at the origin, and it increases away from the origin. And what we'll see, the effect of that is as we attenuate frequencies that are close to the origin. But I'm getting a little bit ahead of myself there. Okay, let's look at the Fourier transform of the rectangle function. So recall that the one-dimensional rectangle had a Fourier pair of a sinc function. The two-dimensional rectangle, which is the product of these two, has essentially a sinc function in 2 dimensions, where these lobes, could be different depending on the size of the rectangle in both dimensions. Here's an example of an image with a rectangle, and this guy here is its transform. So we have different frequencies of those lobes in horizontal and vertical directions. So the lobes are much closer together this way, so they're closer to the origin, meaning lower frequency, and that's because the size of this object is larger in this direction. The lobes this way, the zeros here you can see are more widely spaced, so they're higher frequencies, and that's because the dimensions of this object is much smaller in the horizontal direction. This shows the effect of translating the function. We get essentially the same thing, except, recall that the effect of translation was to multiply the transform values at each point by e to the minus j something. So if we take the absolute value or spectrum, basically that component we multiply by is just wiped out. It's just a 1. So it looks identical. The spectrum looks identical to the transform when the object was not shifted. If we rotate the object, let's say in 45 degrees, that rotates the spectrum by the same amount. Finally, the convolution theorem is very important. It says that convolution in one domain is equivalent to multiplication in the other domain. So if I have a filter, let's say small h, xy, convolved with an image f of xy, that has a Fourier pair of the transform of the filter h of xy, big H, multiplied point by point times the transform of the image, capital F of uv. And you can go the other way. A convolution in the frequency domain is equivalent to point by point multiplication in the spatial domain. Correlation turns out to be the same theorem, except we put a complex conjugate on one of them. And this shows the proof of that in one dimension, just plugging the definition of a convolution into the definition of a Fourier transform, and we get that the result is just the product of h of u times f of u. So this is a summary of all the properties we've seen so far: linearity, translation, rotation. Here's the convolution theorem. Here are those Fourier pairs of sine, cosine, rectangle, differentiation, and Gaussian.